Hello and welcome to this video where we'll come into Random Forest and XGBoost. So here we'll learn about the theory and intuition behind these algorithms. These are the state-of-the-art algorithms for working with tabular data. So this will be really interesting, and afterwards, when you've learned about the theory and intuition, you can go ahead and watch the hands-on video to learn how to apply this in code using scikit-learn and Python. So let's move on to the slides now. So improving the performance of decision tree by combining many trees using Random Forest and XGBoost. So now we have talked about decision trees before and about their low performance but high interpretability. And now it's time for us to combine many trees to create a forest. So let's see how that is done. So starting with decision tree, we have bagging to sample multiple datasets for multiple trees. Okay, what does this mean? Let's see. So decision trees, we start there. It's very interpretable, as we saw before. It can be visualized, as we've seen as well, and that is pretty nice. There's no need to scale the data. We can handle qualitative variable. So qualitative and quantitative variables, it can be handled directly with decision trees. The negative part is that it has low predictive performance. It cannot predict very well. So that is an issue. So how do we deal with this? So we can improve it by combining many decision trees. So combine many decision trees to get an ensemble. An ensemble is a combination of many. So together, a combination of many trees. So we can do that using something called bagging. Bagging means that we sample from the same dataset multiple times. So we have a dataset, we sample from it, we take a subset from it many times. So this is bootstrapping. It's not bagging, it's bootstrapping. Then for bagging, we predict on each bootstrap dataset and do an average. So basically you have a dataset, you bootstrap from it, so you pick out a lot of different samples from it. And then you predict on each of the bootstrap dataset, and then you take an average of it. This is bagging. In case of a classifier, you take the majority vote in the classifier. So, for example, you have a 6 that is saying that this should be a 1, and 5 that this should be a 0. Then it will be predicted as a 1. So how it looks like figuratively is that you have a dataset, you divide it into several subsets, and for that you grow several different trees, several decision trees. Those have different types of answers. They have different type of, in case of regression, different types of values. In case of a classifier, they have different types of classes that it predicts to. Then you do average or you do a majority vote. And then we move on to something called Random Forest. What this is that you build the decision trees on bootstrap training sets. And every split in tree is based on random choice of predictors. So every split in the tree is based on a random choice of predictors. So a predictor is the features. You have a random set of features. You pick up a few of them each time, and then you grow your tree. And you do the split. So then you get a lot of different trees with a lot of different predictions. And then, so that was Random Forest. And then you have boosting, which means that we have boosting performance by growing trees based on info from previously grown trees. So what you have is that you have trees grown sequentially. Each attacks the residuals, the error, improving where it previously performed badly. That you grow one tree at a time, and then you see, if we tweak this tree in this way, then we can decrease the error even more, and on and forth. So we grow several trees in sequences. So this is a boosting. The trees become better and better at reducing the error. That is the idea. So then it means that it will learn slowly. And then you have different hyperparameters. You have a number of trees to overfit if too large. It overfits if it's too large. You have too many trees. So then the model becomes more and more complex because you have many trees on the small data set that you have if you have too much trees. There's also a shrinkage parameter, lambda, that controls the learning rate. So it means that it will learn slower if you have a higher lambda. And then you have number of splits, d, in each tree. This controls the complexity. So d equals 1 usually works well. It gives number of splits in the trees. Then for XGBoost, we talked about boosting. XGBoost is extreme gradient boosting, and it's a gradient boosting like before and with regularization as well. So we talked about regularization L1 and L2 in previous regularization, linear regularization video. And here we add this regularization into the gradient boosting, that it makes sure to punish the weights. It reduces overfitting. This increases the efficiency also in XGBoost compared to normal gradient boosting, and it increases performance. XGBoost is among the top. XGBoost and Random Forest are among the top state-of-the-art for tabular data. They can handle missing data as well. Okay, short note on trees. So decision trees, they are interpretable but low performance. Random Forest and Boost combines many decision trees to improve the performance. Random Forest and Boost are among the state-of-the-art algorithms for data. Also, something to note is that in cases you might combine several algorithms. So you may be combining trees with something else, and you can combine the several trees. You can also do some kind of ensemble, and you can do some majority voting, etc. So this is something to note. Yes. So in this video, we have gone through some basic intuition and theory about how Random Forest and XGBoost work. That it's a combination of a lot of decision trees in order to improve the performance, but we lose the interpretability in a way. So that there's still ways to make it interpretable, but not out of the box, such as in decision trees. So that is something to note. This is an important topic, and also note that these are among the top performant state-of-the-art algorithms for tabular data. Keep that in mind and don't go ahead with a lot of fancy models immediately. Instead, this can be used as baselines. Thank you for watching this video, and see you in the next one. Hope that you learned a lot.